Hello, good morning. Welcome, one and all. I would take this opportunity to wholeheartedly welcome you once again for this session, which is the second day of our REFCOLD India Virtual Expo, October 2020. Yes, today we'll be discussing refrigeration at length, and we'll be talking about a lot of other upcoming technological advancements that have happened over the past decades in this particular field. But before we begin, I would like to request you all to take a peek at the latest publication, which is all about insulation by ISHRE, and get yourself acquainted to the knowledge base of insulation, particularly in building and construction sector. Thank you for taking a peek at insulation and its technical know-how. And I would also request you to take a look at the other publications that are available at ISHRE platform, and please acquaint yourself with the knowledge that is available in the heating ventilation industry, because this ISHRE as a platform can be utilized because it is resourceful. We have been working on research and various other verticals since a couple of years now. Apart from that, I would also like to request you to visit the virtual expo, the kiosks and the exhibition that is available parallel to the workshops, to make yourself aware of the products that are available for you to utilize commercially in the HVAC industry. We would now proceed towards the detail of the session that is about to happen. Ladies and gentlemen, let's take this opportunity to welcome the speaker of the day, Mr. Vivek Pandey, who is the co-founder and chief technical officer at Ecozen. He's into energy conservation through renewable technologies for cold storage, and that is what he is going to discuss with us at length today. He is an alumnus of the Indian Institute of Technology, Kharagpur, and leads design and engineering at Ecozen. Vivek takes a data and physics driven approach to design and has built hardware, AI web, and mobile based technologies for Ecozen's products from the ground up. Ecozen has won several awards at various technology and business and social forums, including ones by the Ashton UK, IIMA, IITB, Confederation of Indian Industries, and Caltech. Without wasting much of time, I would like to request Vivek ji to begin with the session. Sir, your audience.
Hello, everyone. Thank you, Shruti, for that introduction. And it's a pleasure to be here. Thank you, ISHRE and REFCOLD, for this opportunity to be speaking at this workshop. I think basis, the topic that we have at hand, energy conservation in renewable energy powered cold storage systems. So I would basically, what I'll do is I'll go through, I'll take you through a presentation that I put together that talks about clean technology in general with respect to how energy is utilized from renewable energy sources, specifically using solar power. And this comes from some of the experiences that I've had through working with Ecozen as a part of the founding team of Ecozen, leading the technology side of things at Ecozen. I think I'll jump straight to the point here. That I'll be covering is clean technology for refrigeration systems. Basic topics covered in no particular order as such are basically an introduction of renewable energy in general. What kind of clean technology systems exist today, which could be feasible for refrigeration systems in general. How can renewables be used as a as a source of energy for cooling applications. The kind of storage technologies which are prevalent today with respect to refrigeration, storage as in energy storage technologies, what kind of design approach is required to design a renewable energy powered system. Like I said, majority of my discussions will hover around solar PV as a power source for technology, for the power source of powering the cold storage systems. I'll also touch upon briefly about how data analytics plays a great role in terms of conservation of energy, maintaining energy efficiency in general, and talk about a few cases where we just see the commercial treatment of a solar powered PV system along with an energy storage system that is a thermal energy storage. Okay, so I just like this line that was said a century ago, maybe by Thomas Alva Edison, one of the pioneers in the energy domain, pretty much a founder of electricity. And he said that I'd put my money on the sun and solar energy and what a power source it is, and that holds true. And even after such a long time that we are sitting here, this is probably only a decade where this has become a reality in its true sense, when solar is being utilized as a power source for in commercial applications, right? So if I talk about refrigeration systems in general, refrigeration systems tend to consume a huge amount of power, space cooling, including air conditioning, including storage of commodities like fruits, vegetables, and other perishables, storage of pharmaceuticals and other critical items which are consumed by us on a day-to-day basis. They account for a huge chunk of the percentage of energy that is generated. A huge chunk of that goes into cooling. And with time, it has been just growing drastically. Majority of it is happening because of how the developing countries are in the growth phase with respect to their development. That spending on energy is much higher as the economy is moving toward consumerism. More and more people are consuming products which require refrigeration, want an air conditioned environment that they live in. At the same time, the environment is also changing with time. There is a general rise in temperatures in cities, where earlier it used to be slightly cooler, but with time the cities are also getting hotter, and that calls for better refrigeration systems in general, right? If you can see some figures, the food consumption in general has also increased, and as that increases, as the population increases, the food consumption in general increases. The wastages that happen because of correct type of refrigeration systems not present everywhere, billions of tons of wastages happen, and that is expected to grow at a significant rate, like you can see on the slide over here. In general, we all know that rampant usage of the conventional sources of energy is leading to climate change, and that's kind of a vicious cycle. So as the climate changes, as the temperature of the entire Earth on an average increases, that leads to actually more consumption of refrigeration energy, which it essentially means that you are spending more energy, so you are throwing away more amount of heat, rejecting more amount of heat which is getting trapped. You're actually using more amount of fossil fuels, more amount of refrigerant, which are not really good for the environment, are also being thrown in the environment, making it more and more hotter. So it's kind of it keeps adding up, and as our requirement changes with time, that becomes a bigger problem, and a faster and requires a faster solution in general, right? And so like we see that in general, the space cooling will grow threefold between 2016 and 50, and 50 is not very far away from here. If you look at the amount of energy that an air conditioning ecosystem that utilizes used to be 300 ton watt hours in thermal watt hours in 2000, which will become more than 10x in 2050. which is an alarming situation, calls for some kind of changes that we do in our regular practice of how we utilize energy to tackle this particular problem. Right. With this, global emissions of carbon dioxide also increase. In general, these cold storages, the technologies used for storage of fruits, vegetables, flowers, ice creams, meat, poultry, and a lot of other commodities require cold storages, require pack houses, reefer vehicles, ripening chambers. And if you look just in the Indian context, this is set to change very significantly in the next 7 to 8 years, right? You can see the graph over here. The overall consumption or the emissions of carbon dioxide is set to grow by 2.5 times in the next 7 to 8 years, which is a problem to be solved. And I think we are at a situation where we do have ideas in mind as to how to solve them. It just requires a better reach, better understanding of how these technologies work. And, I think we can definitely get there. Talking about renewable energy, I think most of us over here might know that there are several sources that nature provides to us, which can be utilized directly to generate electricity. Some of them are already utilized in terms of hydraulic power plants being very, very popular as a source of energy. If utilized sustainably, turns out to be a great resource. However, it possesses its own problem. But solar as a power source in general has come up very, very fast in the commercial settings, where you can see solar panels now pretty much everywhere. Every city you visit, you might just see a solar power plant in the outskirts of the city. Sometimes in the airports, you might see solar panels being installed at the top of the roofs of buildings. Solar thermal systems being used for water heating purposes. Wind energy is also something that has been commercialized with time, although with limited success, lesser success than solar. But yeah, it's not too far away from there. Ocean is a great source of energy. It has been, we have definitely tried to tap into tidal power and wave energy from ocean to harness energy. Biomass is a great source of energy, and again, it has to be utilized sustainably. Geothermal is a great source, a naturally existing source of energy, which is a great way of utilizing the Earth's a potential of energy to convert that into various usage, like heating purposes, or for that matter, cooling purposes, or in general, production of electricity to run equipment. Nuclear is a great source of energy. It's hugely power dense, however, poses its own set of challenges. But yeah, a great source of energy to in the longer run for the entire world. So these are some of the technologies that mankind has actually experimented with, worked with, tried to commercialize them, and most of them that we see over here are commercialized at some scale, right? So coming to cooling, specifically with respect to cooling, and when I talk about cooling, our discussions will majorly be focused upon cooling for cold storages, storage systems which are used for storage of fruits and vegetables and flowers and a lot of other perishables like frozen commodities, pharmaceuticals, and more. When I talk about cooling, some of the feasible cooling sources of energy for cooling purposes, and when I talk about these feasible technologies, all the nuclear power can be generated at a centralized place, and that can feed a cold storage in the end. I'm mostly talking about decentralized power systems, where the power, the source of energy itself is located in the vicinity of the place where the consumption is happening. And so if you look at the kinds of refrigeration systems that exist, which are popular, are vapor compression systems, one of the most popular cooling systems that are available today. And vapor compression, as a technology that really works, really is robust, has proven over hundreds of years now, used in your air conditioners, your refrigerators, in any typical cold storage system. The vapor compression as a technology is very, very popular. That requires electricity to be generated in order for a motor to run. that motor basically compresses a particular fluid, and a cycle of refrigeration runs to produce the cooling, to reject the heat from the entire system to produce the right cooling required. Although not very popular, but thermoelectric in general is a technology which is also can be, where electricity can be used to produce cooling directly. However, these systems are highly inefficient for most of the cases. However, wherever there are there are cases where they can really be feasible to produce uh, cooling. So for places where electricity in general is required, the majority of these systems, have the majority of the energy sources that we have seen today are either solar PV systems, wind energy systems, and fuel cell systems. And a fuel cell is maybe getting popular slowly. I think in India we have just seen one car which was developed with the help of KPIT and CSIR. It has just been experimented with, and it looks like there could be a future over there. Not very popular at this point, primarily because of the cost and the hazard associated with handling hydrogen as a fuel. Cooling can also be achieved through generation of heat, and by heating you can still run a cycle, and that is how you keep running a cycle to produce to reject some of the heat from the system to produce cooling. And vapor absorption system is one of the most popular systems where heat can be utilized to run a vapor absorption cycle. um, and there is another technology called steam jet refrigeration, which can also be utilized when you have ample amount of heat available for this. And if you look at some of the technologies which are really popular in terms of generation of heat to enable cooling, are solar thermal systems, where while in case of PV systems, we utilize sunlight to generate electricity. In case of solar thermal systems, we do not really utilize the sunlight, but the heat that is contained with the sunlight, we harness that and heat a particular fluid to utilize that into some kind of application. Could be as simple as just water heating as a replacement of your geyser, but can be also utilized to produce higher temperatures and hence run a cooling cycle. Geothermal energy is a great source of energy which can be utilized only at places where geothermal is abundantly available. Even in regular scenarios, geothermal can be used as an energy efficiency system, where the fact that the energy can be absorbed by Earth can be utilized in terms of making your cooling systems better in terms of efficiency. But there are systems where there are places where heat is naturally produced from the Earth, like geysers and places like that, where this can be utilized to produce energy. Biomass-based heat generation is also a power source which is getting quite popular. We have seen some companies even in India which are making cold storages by utilizing biomass as a power source. Right. So if I have to talk about how to approach this entire design problem in terms of utilizing a renewable energy power source to produce cooling, right? So availability is one of the main constraints of whether a renewable energy power source can be utilized at a particular place or not. And solar PV, for example, won't really work in areas where it's always cloudy. It's since we are not really utilizing the heat of the sun, but we are utilizing the sunlight from the solar from the sun to produce electricity. We need to ensure that we are at a place where there is ample sunlight, and India in general is a great place for producing solar. Tropic of Cancer passes through us, and the majority part of India is a good place to generate solar energy in general. However, there are cases where some parts of the Northeast, in some cases where hills are present in the north, there are situations when solar is not really utilized very, very well, but majority of the places in India, including higher altitude places like Ladakh, great amount of sunlight over there to utilize sun as a power source to produce electricity over there. Solar thermal systems would definitely work relatively better for at places where the environmental temperature is slightly higher, and that requires that kind of environment. At the same time, it also requires an ample amount of area to capture that energy, right? And having that area is not really a trivial task to achieve when it comes to refrigeration systems, because if we are trying to do this in an environment which is basically not a remote it's basically a city location, that kind of real estate actually costs money, so that has to be considered while designing such systems. So wind turbines, again, similar kind of issues, but they become really, really viable in places where there is very good wind velocity present. It's generally very good for higher altitude places. However, there are technologies which, for example, micro turbine technologies, where there is an array of wind turbines which can be used even at a place where the wind velocity is relatively lower to produce electricity. And some of these technologies can work really well in complementing each other. For example, in case of solar PV systems, if it is hybridized with a wind system, sometimes it works the best, because there will always be cases where solar PV is not able to generate electricity all the time, and wind can complement at least on those times when solar is not present. Again, one of the most the second most important consideration is also the cost of these technologies, implementing these technologies. And when we talk about cost, solar PV is at a place where when we got into business, I entered into solar. I did not really have a lot of knowledge of solar, I being a mechanical engineer. But back in 2012 or so, when I got into solar, the cost of solar panels were still as high as maybe 60 rupees or 70 rupees per watt peak. And today that has come down to, and these are for good quality solar panels, they have come down to maybe 16 or 17 rupees per watt peak, which is a drastic change in terms of how solar PV has become more and more prevalent, thanks to a lot of policy level changes that the government has brought in over time to enable this to happen, to make sure that the manufacturers are producing more and more, and their cost of production is going down. With time, the energy efficiency of these solar panels have also changed. Most of the solar panels earlier, although I wouldn't say that it has changed dramatically, from maybe 13% or 14%, we have the costs that I'm talking about, they may have come to about 18% or 19%. There is a long way to go over there as well. A lot of research has been done, but yeah, we're still to get there. But the cost is one of the considerations that we need to consider when choosing a technology over there. Now, given the fact that in general, renewable energy as a power source are complex and hence a little costlier than conventional power source, energy efficiency becomes one of the biggest questions or biggest problems to tackle while designing such systems. And the reason for that is, every unit of electricity extra that you utilize will cost you in the capital expenditure that we are making in putting the renewable energy systems together. For example, there are cases where a lot of cold rooms, which are small scale cold rooms, will be fitted with 60 mm of PUF, an insulation material, polyurethane foam. However, if you are talking about renewable energy based systems, you'll try to optimize the amount of insulation that you use, which will ultimately dictate the amount of, not directly, but at least in parts, it will dictate the amount of solar panels that you utilize. There has to be a kind of trade-off between the two when selecting the number of solar panels and then the amount of insulation that we use. Right, and so the cost and feasibility trade-offs have to be evaluated during this period. Refrigerants directly affect the efficiencies of the systems as well. If you look at some refrigerants, some of the refrigerants which have been phased out, in fact, have much greater efficiency as compared to some of the more modern refrigerant that have come up. However, there are cases where, for example, R22 is highly efficient in terms of in a vapor compression system, but pretty much being phased out as we speak. It has been done the most of India, most of the world, slowly getting phased out in India as well. But the right refrigerant for the kind of temperatures that you are working with is very important with respect to the energy efficiency we're talking about. Type of compressor, again, several types of compressors have come into picture today, and so one part of a compressor is the compression technology itself, the way you compress. Reciprocating engines have been very, very popular in the past, and now there are other and screw compressors and scroll compressors which have a different working principle as to how the gases are compressed. So that is one part, and the second part is the kind of motor technology which is used in this entire system, right? A lot of us must have seen these inverter air conditioners. People call it inverter air conditioners that have come into picture, and the reason for that is, although the refrigeration, the compression part of the motor of the entire compressor remains the same, the motor part of it has changed. A lot of these inverter compressors use something called a BLDC compressor, which is a brushless DC compressor, much more efficient than your induction compressor, which run directly with a 3-phase or a single phase supply, 50 hertz supply. But in these cases, you basically feed in power, which is then conditioned to a different kind of power. The frequency of those of the power supply to a BLDC motor will be different, and that gives us a near synchronous kind of operation of the motor, and because of which we are able to save on losses that we have we make in case of induction motors. In general, if there is another technology called permanent magnet synchronous motors, BLDC would be a subset of that. And these are highly efficient motors. The motor efficiency, even for a 3 HP or 5 HP system, can go as high as 91, 92%. However, even an IE4 motor of induction technology would be somewhere around 75, 80%. And becomes very important, although you end up there are incurring more costs in making these motors. One of the reasons for that is we use magnets in these systems. There are two risks associated with that. One is that magnets in general are the magnetization potential of magnets are the best for ferrite magnets, and these ferrite magnets are produced. In India, they are very small in terms of production, and China controls a majority of that. Production. There are some production in Europe, some in Australia, but China controls majority of it. Right? So that must also be considered while selecting a system, while thinking about future in general with respect to refrigeration systems. However, there are alternatives available. For example, I'm sorry, I'll correct myself. So basically, we use something, these technologies, these motors, BLDC or PMSN, typically use something called a rare earth magnet. And ferrite magnets are something that can be used in an alternative, although they have lesser magnetization density, but they can still be utilized to get the same effect of energy efficiency. So that compressor type, selecting the kind of motor, and then the compression technology becomes important. The way you design the refrigeration cycle, right? In a vapor compression system, it's basically you have a compression system, and then the gas moves to a condenser, and then you have a kind of metering device which will bring down the temperature, which will basically expand the gas to make the gas bring at lower temperature, and then there will be a place, an evaporator, where the heat will be absorbed, and the cycle continues. But in general, if you are an engineer, know a little more about practical refrigeration systems, there are more considerations with respect to how refrigeration cycles can be modified to make them more and more efficient. For example, useless superheat in evaporator can be utilized to make your condensers more efficient in terms of the exchange of heat, right? And So these are some of the things that which can be used. The kind of the cooling method of the condenser that you use varies depending on the sizing of the system and the place that you are at. An air cooling system may work best for some scenarios. A water cooling system may work the best for other scenarios. So that also has to be considered. The way we do capacity control, so two things over here, especially with respect to renewable energy. If you are trying to utilize systems, which is a system which is, let's say, a solar powered system, a solar PV system, you will end up generating very small amount of power in the early morning times when the sun is just rising, and the peak power will come in only when the sun is overhead or directly facing the solar panels themselves. So you basically are running your compressors. If the system is designed such that the compressor is run directly with the solar power that is coming in, we have a variation in the speed of the motor. And hence the amount of refrigeration produced will vary with time. There could be other cases where we store energy in a battery bank, which makes the system slightly less efficient, but we can still keep running the compressor at the same speed. But if we are talking about a more efficient system where directly the solar energy can be pumped into the motor and the motor runs at variable frequencies, there is and there is another angle of management of how you manage the evaporator capacity, and overall. So if you are generating lesser amount of cooling, you need to ensure that we are also consuming a similar rejecting similar amount of heat, and hence ensuring that there are the system is designed such that it is able to maintain cooling at all points of time. However, the system is generating only a fraction of the total system capacity at any point of time. So that capacity control, coupled with other technologies like suction pressure control, etc., can give us more and more energy efficiency. Some other things like waste heat recovery, maintenance of the system becomes very, very important. And depending on where we are, solar panels tend to get very, very dirty sometimes. There has to be a mechanism to know whether the solar producing power panels are producing the right power or not, whether condensers are working at the right capacity or not. So cleaning the condensers, cleaning of solar panels, they become very, very important when it comes to maintaining energy efficiency of the system. Right. Leakages. The way we design insulation, and then the way we build the room, the way we build the doors, the way the curtains are inserted inside the system when you're opening the door to minimize the amount of heat leakage, energy leakage. That becomes extremely important, because now, given that you have a limited power that you are producing, you need to make sure that we are not losing it as much as possible, at least. And then there are like other electrical characteristics of things like even fan motor, right? Fans are one of the after compressor, fans would be the next major energy guzzlers. And if we can use more efficient fans, and there are several technologies again available in case of induction motors. There is something called electronically controlled fans, or there are VFD technologies that run a three-phase AC fan to ensure that we are not really using something called an on-off control, where you switch on the motor and then switch it off. Instead of that, you run it such that the efficiency of these systems are very high, because now you are modulating the speed at which the fans run. Similarly, fans can also have a different kind of motor, a permanent magnet motor, which can give you much more efficiency. Now, so if I talk about, there are two major cases that I'll talk about, and one of them being a solar PV based system, where solar power in general is used as a kind of power generation system in a captive mode, in the sense that there is a cold storage establishment already available or is being built, is being planned. It could be 1,000 metric ton cold room or 5,000 metric ton cold room, large surface area present on the rooftop or nearby areas where solar panels can be put. And the way they can work, and this depends very much on the kind of scenarios there are locally, is that there is one case where solar PV, basically sunlights fall on the solar panels generate electricity, that electricity can be fed directly to the grid of the entire cold storage system, and that energy is utilized right then and there. If there is an excess power available at any point of time which you are not able to utilize at some point of time in the day, that electricity can be exported back to the grid, and the government pays you back because you are now supplying electricity to the rest of the country. And in cases where there is a deficit in amount of power that you are generating, you are pulling energy from the grid and you are paying for that. Essentially what you end up doing is reducing the amount of electricity bills that you pay, and being able to generate the amount of electricity that you can with a given amount of solar panels, or the given amount of rooftop surface area, or the real estate area where you put solar panels. So that can be utilized. Another method, and where if we want to utilize solar powered system as a standalone system, which is or in cases we want to utilize such that if there is electricity shortage, or there is an electricity cutoff, the grid goes down, we are still able to run cooling without having to use, let's say, a diesel generator set, which is a typical way a cold storage system is designed, right? So over there, what you do is you basically have an inverter kind of system where a DC electricity is generated from the solar panels, is fed into a battery charger that will charge the battery. At the same time, there will be an inverter present to convert that into AC, depending on of course, depending on the kind of compressor that you have, or the power system that you have. Typically, generally, AC systems are very popular, so I'll assume that inverters have to be used to be inverted from DC to AC, and that is how it can be utilized. So whenever power is present, ample solar power is present, the inverter directly supplies an energy to the the cold storage machinery. And in cases where there is a shortage of electricity, the battery banks, which are charged already, can start supplying electricity to the entire system. There is a third method where we can use solar power to generate energy such that it satisfies the cooling need at that point of time, and the excess of solar energy, if at all, is put in something called a thermal storage system, which is essentially a phase change material kind of system, something like a very big ice bank. You freeze that water, make them ice, pass, make heat exchanges such that cold water keeps circulating throughout the building through that thermal storage system. Two ways that helps. One is, of course, you are able to use that as a buffer, as a replacement of battery. And second is that there are cases where there is something called a differential tariff applicable in places where if you have, even though you have solar, you are still using electricity, but then there are times of the day where the electricity costs are higher. At that point of the time, you will run the refrigeration system with your thermal energy storage backup. In the rest of the times, you will utilize the grid electricity to charge the entire thermal energy storage. And solar PV can be used as an add-on to the system to make sure that you are reducing the amount of electricity that you are consuming even further. There is another use case where, and this is something that I have worked upon, and we have made products that are out there being used by people, where you have solar panels, and you basically convert, you generate electricity, convert it such that it can run a compression system, a vapor compression engine. At the same time, while you are you are pumping that energy into a compression system, there will be times of the day where there will be an excess generation of power. So the system will be designed such that it is able to give a bare minimum amount of cooling for the room cooling to happen. But at the same time, given that this is a standalone system where there is no other power source present unless it's absolutely required, in those cases we would need to have a thermal storage or a backup system present over there. What I have done with our Ecozen products is basically a fission material-based system. However, there are a lot of cases where people use this excess energy to be put inside batteries. Those batteries then will convert the chemical energy stored in them to electricity, and that will keep running the entire system cold for the for 24/7, even when solar is not present. Given that solar is just present only for 10 to 11 hours in a day, we need some kind of backup system, and there could be two different methods. One is a PCM based thermal storage, and second could be a battery based system. However, there is a small amount of battery always required, because there are systems which are commercially, there are things which are commercially available, things like valves and fans that require electricity to be run. And the reason why a PCM based thermal storage has to be can be utilized over here is that it's ultimately cooling that you want to do. So why not cool earlier than you really need to cool the system, utilize that cooling energy that you have stored at a later point of time to keep the entire system cold. But at the same time, since fans and control systems and the auxiliary things like lights, etc., will require some kind of electricity, there is a small amount of backup battery supply that can also be done. Battery energy that can also be stored over there. So this is something that I was explaining that if we are sizing the system, we size it such that this is the amount of energy that we have. This is the heat load that we have is this, and this excess amount of energy that we have present. This goes into something called a thermal storage system, or something like a battery management system, where it is stored either in form of chemical energy or in form of thermal energy, and this energy should be sufficient enough for you to give you a stipulated amount of backup. And typically, when we think about solar systems in general, we at least make sure that today, when the day ends, I should be able to keep the entire system cool until the next sunrise. However, we should also have this, explore this possibility of having the next entire day, and that is a worst case scenario, that the entire next day there will be zero production of solar. If that happens, and size the solar panels, the amount of solar panels such that this can really be removed. Sorry, my mouse is not really, just a moment. Okay. Okay, all right. So move to the next slide. Okay, so one of the important things that I wanted to touch upon is that, of course, selection of components, doing heat load calculations, selection of components, coupled with the energy efficiency techniques that we talked about. That's something that people would know about, I'm assuming, and we have been doing that conventionally for a lot of cold storage systems. However, in case of renewable energy, there are a few more things that definitely matter. So one was definitely the matching of energy balance, the doing the right energy balance, so that we are able to provide backup even in like worst of the scenarios. If we are, let's say, designing the system such that it runs very well for 300 days in a year, in those, the worst of the 300 days, how should the solar panels be sized such that it can still provide cooling for, say, 36 hours without having any other power source? So that is very, very important, and that can be done. I'll maybe talk about a little bit about data analytics and coupling that with the typical heat load calculation systems to achieve that. But in case of solar PV systems, another thing that that I wanted to touch upon at least was having solar panels at the correct angles. So if you look at any conventional, if you talk to a solar professional, any professional who has been into the solar space, they install solar panels for, say, pumping applications or rooftop solar generation systems for home applications, etc. There are some general thumb rules that exist. Even in the power plants, there will be some thumb rules that will exist. One is that there can be technologies that can be utilized which track the sun at all points of time, right? Be it any season, any day, the system, the control systems of that system will try to make sure the solar panels always face the side of the sun, right? The azimuth angle and the elevation angle is such that it always faces the sun, so that the normal irradiance that is coming to the solar panels are the maximum at all points of time. So basically, we're trying to utilize as much as possible, and that really gives much better efficiency or much better harnessing of solar power. If you look at general thumb rules, maybe even a 1 kilowatt solar panel, if on a particular day it will generate let's say 5 units of electricity, a very well tracked solar panel can even generate 6 to 7 units of electricity. There are other situations where you do this tracking on a single axis, where the elevation can be adjusted in different seasons. For example, in winters it can be tilted more and more, in summers it can be more flatter, and at the same time during the day we keep tracking the sun as much as possible, and that also gives us better efficiency, better generation of solar panels, at least maybe like 15% or 20% if the solar panels are clean. However, these tracking systems are extremely expensive. Two things. One is that they have to be extremely reliable, because they are moving parts. They are moving all the time. They are hydraulically powered systems typically, and require energy to be run as well. So typically they're expensive. They have precise control systems going into them, a motor going into them, and a load bearing the rod, at least, or a load bearing member, which is actually holding this entire piece together and moving it, is also going in that system. It typically is expensive. At least people who sell this commercially, it's quite expensive. Maybe the cost can be brought down, but the reality is that they are expensive and not extremely popular. So most of the installations that we'll see will have a fixed angle kind of installation. Then when you're trying to fix an angle, there is a general thumb rule in solar industry that we'll fix it at I'm talking about the elevation. With that, the entire solar panels, the set of solar panels will face south. We are present for the Indian location. They'll face south, and the tilt of the solar panel is such that the latitude of the place, for example, if I'm sitting at the Tropic of Cancer, about 23 degrees, I'll try to keep the solar panel angles at 23 degrees facing south, and that works well. And that works well in terms of overall. If you look at the entire picture of throughout the year, that is an angle. It may not be the best angle. There could be better methods to estimate that angle. Would be, that answer will come close to latitude angles, but that will be a good angle to generate electricity. Okay. However, generate electricity for regular usages. However, when it comes to solar power for cooling purposes, there should be other considerations to be kept in mind, and that also helps with maybe reducing the amount of solar panels that you will end up utilizing. And the reason for that is you are utilizing these solar panels to cool the system, right? Which essentially means that and your cooling requirement depends directly on the environment temperature. So this environment temperature, the way it plays a role is that the efficiency of solar panels are much lower at higher ambient temperatures. When the cell temperatures go high, the efficiency of the solar panels go down as well. When the cell temperatures are low, they are very, very high. Right. When we are trying to tilt the system, the angle such that they are tilting at a latitude angle, they will probably work very well for, let's say, winter conditions, where and I'm talking about, maybe some places, may not be true for all the places, because it totally depends on the sun path at any point of time in the year. But in general, if you try to see, maybe do an analysis on what will be the number of deficit days for which the solar may not be sufficient enough for any given amount of solar that I'm utilizing may not be even, and my goal is to achieve, let's say, 300 days of cooling, and in what situations will my number of solar panels, the given set of solar panels will be producing this energy at a certain angle. And doing that analysis will actually give a picture that, okay, the heat load is going to be lower in winter conditions. So it's better that we are trying to optimize better for summer conditions, right? And in summers, since the sun path is majorly, it moves a little more vertical than at an angle, the sun in general. So it makes sense that the solar panels are flatter, right? So typically, with the answer that comes out in this analysis, and I think less number of people would have gone into that level of getting in the right correct angle of solar panels, is that it is going to be much lower than the latitude angle. Okay, it will be maybe closer to 0 degrees, to flatness, and maybe like 5 degrees or 10 degrees, let's say, for a 23-degree place will work out much better than 23-degree latitude angle. And that is something that needs to be considered when we are designing solar panels, especially for this standalone cooling applications, right? So this is something that needs to be considered. I covered this part. Now, when it comes to renewable energy systems, and especially solar, and many other renewable energy systems, we need to have a storage system in place. In fact, it is true even for something called your hydroelectricity, where we need the water to be stored by using a dam. Or even in the coal power plant, where you need constant supply of coal, right? Over here, since solar is present and that's the reality of the situation for a limited period of time in the day, we need to have an energy storage mechanism. So in the first case, the use case that we talked about, where the solar power plant is being utilized to reduce the amount of energy that you utilize directly from the grid, and hence reduce the electricity cost. An energy storage system may not be relevant over there. It can be directly feeding to the grid, and you are just utilizing the delta amount of energy that needs to be utilized if the solar power production is not sufficient enough to run the machinery at that point of time. However, in most of these standalone systems, we require energy storage systems, right? So if I talk from another experience of solar pumping, what happens with solar pumping is that we don't store any energy in terms of chemical energy, batteries, or anything like that. If we have to, because the simplest way to store in that case is not really storing in a battery kind of system, but maybe storing in a water tank. In the day, size the system such that if you, let's say, require 1 lakh liters in a day, and you are irrigating during the day and even during the night time, and hence you require some kind of energy storage over there, just store as a potential energy in overhead tanks. And that is how that is the most efficient system that can be out there, right? Storage of water instead of storage of electricity, or in form of chemical energy, if you have to just utilize that energy only for watering purposes. Similarly, in the solar PV systems for cooling purposes, one of the interesting technologies, and it has started gaining momentum these days, is a thermal storage system, where you essentially store cooling, because that is what you are going to utilize, and that is what you really need to keep your system cold, instead of using other energy storage systems, which are one of the most popular ones are, of course, lead acid batteries. And a lot of households would have an inverter system with a battery storage system that will provide power during the times when electricity is not there. Lithium-ion batteries are becoming more and more popular as the electric vehicle scenario in the world is changing. I think the lithium ion is going to be cheaper with time. Highly energy dense. Very safe at this point of time, I would say. The nice energy source, has its own limitations in terms of environmental hazard and a lot of other things, but yeah, good energy storage device to be used. Fuel cells, we talked about that, but with time, it will probably gain momentum. There are other methods like magnetic energy storage, liquid air energy storage, and then whatever the large power plant systems store, the way they store the pumped hydro storage and compressed air storage or flywheel based storage. And then there are thermal storage as well. That's a different kind of thermal storage where, if there is a steam engine or an engine that produces electricity using heat, you can utilize thermal storage in a different manner, like in a molten salt state where you are utilizing your storing heat in the system instead of storing cold, and that heat is later utilized to, let's say, boil water and produce steam and then generate electricity. And then there are thermal storage systems where you store either the latent heat or the sensible heat in phase change materials. And essentially what they will do is, and the reason why latent heat is utilized is because there is a big energy, there is a big band where a lot of energy can be pumped inside a material at that particular temperature. So for example, water, when it turns to ice, packs a lot of energy while this cooling happens. So thermal energy storage systems, and if you look commercially, there are two major ways in which this energy storage happens today, are utilized today. And just to maybe clarify this a little bit, a tank storage system, where you essentially, what you do is, there is let's say a tank filled with phase change material, which could be, let's say, water, which could be any other material if you require a different temperature than 0 degrees. It can be water plus salt, it can be water plus glycol, it can be other organic materials as well, where there will be a tank in which these materials are poured, and the refrigeration circuit will charge them, which means essentially freeze them with time. And then in order to utilize them, there is a secondary refrigeration cycle or a secondary loop that will discharge this entire tank and make the cooling reach the space in which the cooling has to be done. A second way is basically storing in a similar manner, maybe not in a tank, but in heat exchangers, which can also, instead of using a secondary refrigeration loop, it will discharge directly by air. Makes it a little more efficient as compared to tanks, but tanks also have their own advantages with them. So these are different kinds of energy storage systems that are used to provide cooling 24/7, especially in standalone renewable energy systems. I'm talking in context of solar power at this point of time. Now, while I talked about different properties of these energy storage systems, there are several considerations that need to be kept in mind while designing these systems. So the key considerations are basically, one of the prime things is basically cost. The cost has to be meeting ER requirements. The life of these systems, again, dependent on cost, because if the life is lower, if you need to replace these things frequently, that ultimately increases the life cycle cost of the entire thing. Okay, let me just check the time once to see where I am. How much time do I have? Okay, so it's 7:32 already. I'll be as quick as possible right now. So we do have a cost and life and efficiency of these systems. When I talk about efficiency, it's basically the amount of energy you basically lose when charging these systems and then discharging them. The volumetric energy density, depending on the kind of space you have, you need to choose the right systems. The specific energy with the amount of weight your entire system can carry. The power transmission rate, how quickly you want to discharge the entire system, or how deep do you want to go in terms of discharging the system. Overall robustness of the technology that you're using, autonomy, control, self-discharge is an important factor also, as in when you don't really require the energy source should be able to keep itself intact as much as possible. Every energy storage device will have some kind of inherent self-discharge because of environmental factors or because of its own properties. Then there is the way you can monitor and control this entire system. Just wanted to talk a little bit about how chemical storage, energy storage, and TES compare with each other with respect to cooling technology. So if you look at a battery system, it can be a lead acid battery. Some of the graphs that you see here is about lead acid or nickel cadmium kind of batteries, where there are some optimal zones that will exist in terms of state of charge, that between 30% and 70% or 80%, this amount of power that can be taken out from the system is quite good. However, and the efficiency is quite good, the round trip efficiency, which is charging and discharging. But that drastically changes as the state of charge changes over time. Also, with time, as the more number of cycles of this charging and discharging and charging and discharging happens, the batteries tend to have increased internal resistance, which essentially lead to more amount of losses in these systems. So batteries definitely have some issues with respect to efficiency. If you look at the lead acid battery, of tubular gel, highly efficient battery meant for operation for 5 years, typically they will have a round trip efficiency of about 75, even maybe lesser than that percent, because there is an inherent loss in the battery charger, the power electronic system that you use to charge, and then there is loss while this DC electricity or AC electricity is being converted into chemical form of storage, and then during discharge the same thing happens. So these are some of the issues. So overall, if you look at it, if you are running, let's imagine a scenario where there is a battery backup, and then there is a scenario where there is a thermal storage backup. What will end up happening is, if you look at the overall system COP, which is the coefficient of performance, batteries will provide a better coefficient of performance, because the system is running as it is even earlier, like the amount of electricity used will be with respect to the amount of energy that is provided to, let's say, the compressor will be utilized at a certain evaporating temperature. However, if you compare that with the thermal storage system, the COP will go down, because you need to ensure that you are charging the battery at the thermal battery at a lower temperature, at a lower evaporating temperature. For example, if it requires 0 degrees, you will charge it at, let's say, -5 degrees. So there is an inherent loss in the cooling cycle's efficiency. However, the overall energy consumption of a battery system will be much higher, because, like I said, 75% is the right round trip efficiency of a lead acid battery. And that too also maybe just a 6 months old battery, and not really even after 3 years it will be more. So these thermal storage systems definitely work better in these scenarios if they are designed properly. So if you compare them, if you look at lithium ion and especially for cooling technologies, a direct PCM based technology or a tank based PCM technology definitely works much better compared to battery technologies in almost every other aspect, except things like power transmission rate or energy density, because the energy density of, let's say, if you're using water, will be much lower than what goes inside a lithium ion battery. But if you don't really have a lot of space or that weight restriction on the system, for example, a PCM system for a mobile refrigeration system would be a tough game to play, because water itself will, if a 12-ton truck, you'll put 1 ton of water itself or a fission material itself, that will that will just drastically reduce the unit economics of a truck itself. So that needs to be thought about. However, works much better in most of the cases for standalone applications, if you talk about the direct PCM systems. Okay, we have crossed the time. Okay, so there are cases I just wanted to touch upon a little bit of data analytics while doing all this. And data analytics comes into picture because when you're trying to use physics to estimate system properties or system design or component selection, there are cases where we do very ideal calculations and we end up either oversizing the system, sometimes even undersizing the system. And if we do a proper heat load modeling coupled with strong data analytics modeling approach, it becomes more and more robust. And it can be, since we do not really have the liberty to go oversize, it makes a lot more sense to analyze things like weather data, ensure that we are optimizing insulation and power and the backup energy requirement, and the size of the compressor itself, and the overall component sizing in general. It's extremely important for the energy to be utilized properly or generated properly. It's extremely important to monitor how the systems are operating, and IoT plays a big role over there to ensure that we are able to get the right information at the right time. And the data that we can pull from these systems can tell us a lot about how the systems are performing over time, how they are deteriorating over time, and what can be done to predict issues, or even diagnose issues if issues have occurred. Like I said, solar panel cleaning or compressor vibration or condenser cleaning are important factors, and those can be done directly through data analytics. Some of the things like compressor vibration, etc., or the estimation of the right estimation of backup, so that you are not ending up spoiling your produce, is something that becomes very important as well. There are other problem statements that can also be tackled using data analytics. Things like, if there is minor leakage in the system, how can data be leveraged to ensure that we are able to diagnose it before even the backup runs out, right? And ensure that overall cost of service is basically lower. Given that we are in an age, which is an internet age, we should try to leverage things that help us much better, and making systems more and more smart makes a lot of sense. And some of the web and mobile technologies can be utilized for the same thing. I think one of the prime questions that definitely comes into mind when you talk about a solar powered system is that the capex is very, very high, and I would tell you that, like I started saying, that the costs were very high earlier, and at this point of time we are, if you look at solar power plants, big solar plant, megawatt solar power plants, the rate at which the electricity from those power plants are sold are much lower than the rate of electricity that you are charged at your homes, which means that we are now doing better in terms of coal or hydroelectric power in terms of solar, and the payback period of solar energy has become more and more lucrative. In case of a standalone system, where you just not really standalone, but a captive power generation system, where you have a large energy requirement, you are putting sub solar panels to reduce electricity bill. If you see these calculations, approximately the payback will be 2 to 3 years. In a small scale system that I talked at length about, an additional cost that you will probably incur for making this system, conventional 5-ton cold storage will cost about 4.5 lakhs. A system with a solar power system along with thermal storage will probably cost somewhere around 8.2 lakh. These are some rough calculations with some assumptions. So, but if you see the delta amount, which is about 3.7 lakhs, it can be paid back very, very quickly, maybe in less than 4 years. And if you take the opportunity cost in mind, which is basically things like a cold room could not be deployed in an area where there was only 8 hours of electricity, which is generally the case everywhere in India, even though we call it highly electrified now. In rural areas, in agricultural places, wherever agriculture is really happening, we get maybe 8 hours of electricity at max in terms of 3-phase electricity. And over there, if you are able to put a cold room, the amount of value that we are able to generate because of having a cold room at place is much more as compared to just saving electricity over there. So the payback period is, it becomes more and more lucrative if we are empowered now with solar as a power source on farm to cool produce right at the start, to pre-cool the produce right at the start of the cold chain itself. This is something that an internal case study that we have, where a flower farmer, turned around better profits. And this is, I'm talking about the opportunity cost, where all of a sudden there was a lot of overproduction in the area. So the person stored the material in the cold room, cooled it, kept it fresh for some time, and the prices jumped by 5 or 6 times in a period of 10 to 12 days. Simply because the production kind of flattened out, and that gives the payback period for that person will be much lower. So yeah, we do have a great potential of utilizing solar as a power source for cooling applications, especially for storage of fruits, vegetables, and other commodities like meat and pharma and fish. I think it's a long time pending that we are adopting these technologies faster for a better future for our planet. Yeah, thank you very much. I think if you have any questions, I'll be happy to answer. And yeah, I'm sorry I exceeded the time a little bit.
That's all right. Thank you, sir, for your valuable time and such an insightful presentation. We do have a lot of questions popping up from the audience end, but I would take the 2 most significant ones at this point of time. So the first question is, How will standalone solar system work on a farm level during rainy seasons?
Okay, so yeah, that's a question that people generally ask if you're trying to go and pitch them a technology that okay, solar power is a power source, use it for cooling purposes at your farm. The problem is that problem can basically be solved in the way that one thing is that during rainy season your heat load is also lower, so you require lesser amount of energy to cool, and you do have some solar power present, and if the system is designed well, that partial generation of power can be again stored and utilized. And the second thing is, majority of the cases in these rainy seasons, there isn't a lot of production. It's majorly the time where you are sowing the produce, or getting the produce to get ready, and right after that you start storing them. So it doesn't become a big problem for the farmers when they try to utilize it. They look at the use case of maybe 10 months for this. Yeah.
All right, thank you. And the next question is, what is the life of a thermal energy storage system?
Yeah, so if you look at so life in general, if the system is designed well, it can be almost over 100 years of life, because these systems are majorly made with things like water, or water plus some chemicals, and then materials like plastics, and then materials like copper and steel. And virtually, if they are designed well, if they are and being utilized and maintained properly, they don't lose their properties over time. So typically 25 to 30 years is an easy estimate with the right design conditions. However, they can also last for much longer time.
Thank you, sir, for touching various verticals of renewable energy utilization in the current day situation. And on this note, I would now request the audience to move towards the exhibition areas and explore what's there in those verticals to discover. Thank you.
Yeah, thank you everyone.
Thank
Bye.
you, sir.